All right, so today's video we're going to be covering Newton-Raphson and kind of transitioning over to the Thomas algorithm with this idea of a tridiagonal matrix. So yeah, let's just get started, honestly, before I start saying things I don't mean. So what is Newton-Raphson? It's kind of a, I don't know, a primitive root solver, if you will. If I can scroll over to this other side here. Okay. So say you have a function that you're trying to get the root of, something like this, and we pick an arbitrary point here. This is our initial guess. If you remember, with root solvers, we always give an initial guess. However, the difference with Newton-Raphson is that usually we iterate guesses based on one initial guess. So you can imagine where there's some error, but we have this initial guess and this value at that initial guess. So we approximate this as a line, the derivative, you could say, of this point. So I don't know if you can see that. Like that. And you notice that we are not hitting any of our roots. So again, our roots are where our function are equal to 0. So notice we don't hit any of the roots, but we try to approximate this x that we hit a 0 at as a root. So since that's not a root, we iterate again at this x. So this is our new x, maybe x1. So we iterate, and then now we do another, I don't know if you can say, the form is similar to a Taylor series expansion, but I don't know. You'll see when I guess I write out the algebra here. But we do another approximating the value as a line. So maybe something like that. And again, we do not hit our 0 there in, I don't know what color that is, gray maybe. So we have another guess, x2 up here this time. And now we're getting closer and closer to that 0 there. So that's the idea. We're trying to iterate guesses, and there's an algebraic form that this takes, similar to the Taylor series expansion we've seen, where I think we went from state space variables into the transfer function. But you imagine where this kind of primitive root solver is iterating guesses, the normal root solver does usually a bracket. I think root scalar does a bracket, and then root can just take, actually I don't even remember, but the point is we can have something where if we guess at a place where the slope is 0, then you can imagine we'd hit a sort of error where we won't be able to hit a 0, or we might get super far away from our desired roots, which are actually quite closer than we might think. So that's the idea. So again, I mentioned the Taylor series expansion. Similarly, we take the value of our function, so we'll call it, I know I put x0 as the initial guess, but it might help to do it in starting from 1, so we can iterate from 1 to 2 to 3, and that makes more sense. So we start at, I'll say x1, and then we add on to that our derivative, which was our, so we took the value of our function, and then we did an approximate value, or we estimated it as a line, the value as a, well, essentially a slope. So we had a slope at that same value, x1, so our current guess or current position, you might say. And then we see, we multiply that by how much we moved by. So we moved by, I don't know, we can do, since we started x1, we do x2 minus the current position x1. So there's this, we're trying to solve for this next iterating function where all of this is equal to 0. We have the current value of the function plus how far was the change, and then how wide did we move by. So trying to isolate it, that iterative term, the next value, we can kind of just move everything to the right-hand side here. So we have x2 minus x1. I don't know if it's where, I'll do it stepwise, so it makes more sense. We have our derivative. It's equal to the negative value of our function. at our guess, initial guess, well, x1 in this case, and then we divide this over, and then we can add this on. So inevitably you will have, for the next iterating value, we have x1 in front, and we can subtract our value of x, or our function at our guess, divided by the slope, x1. So now we have a way of getting this iterative value. So you imagine, I think it said in the topic, we're going to be coding this out. So iterating this through a loop would be the best guess. And with our derivative, in multivariable systems, multi-equation systems, we'll use the Jacobian, but in our case, I think I have a polynomial just with the roots multiplied out here. We'll be using this as the example. I'm pretty sure this is the same one in class too. So we'll be trying to get the roots converged to a root given an initial guess for this polynomial, as well as for our derivative, we'll be using a finite difference, a numerical derivative, if you will. So I have those pages pulled up, and I think we could just go straight to the collab here. So let's do that. All right, so that's the collab. All right, so I should have just, I think I can split here. So let's do that. Let me just copy over. That might be too much. Trying to copy over this polynomial since that's our function. So I'll just drop that here. Oh, will it not let me copy it again? Oh, that's sad. Okay, I'll just type it out. I can move it so x minus 3, so a root at 3. And we have the decimal points to ensure it's a float. And not treat it, so Python doesn't treat it as an integer. Then another root at negative 2.5. So this is just an example problem. You can use any problem. And then x, so a root at 5. All right, so that's our function. That out of the way, go back and full size this. And we can call this Newton-Raphson. I don't know if I spell this right. Who knows? So I think, oh yeah, we need to, yeah, I'll do it now. We do have to use, so I mentioned the Jacobian, so that's the multidimensional equivalent of a derivative. Well, yeah, in multi-dimensions. So we will need to import jax and some other stuff. Will it not let me copy paste this either? Okay, well, that's a good reminder. Since I know what to do now, I can just go over here. I already have it pulled up, but I'll just do it now so I don't forget. We're configuring for 64-bit precision, so that way the precision doesn't kill us when we're using the Jacobian with our arrays. So, well, first we should do import numpy as np, and then import jax.numpy. Can I just do that? As JNP. So hopefully that works. Oh, too many practice sessions. Okay. Let's just do that and run this. So I don't know if that will do anything. I'll probably say X is not defined, but anyways, we'll just start coding this. So we need a function, we need a derivative. So we'll do a function for that as well. Yep. And then we need to do our actual root solver. We'll call it Newton. I think that's what we called it in class. So let's go F1 for our function, and it takes variable x. So that's our function, and then we return that polynomial. Again, we did it in a kind of smart way where we didn't have to multiply it out. We just found the roots, well, arbitrarily picked roots, selected roots, and multiplied them. So we have a polynomial, in this case, x to the third. Then, what else we got to do? So I said derivative. So we'll need a derivative, and then we'll also need the Newton. So Newton function, maybe Newton 1. So I'm labeling it 1 since, again, we have another example where it's nonlinear. So trying to differentiate the two. And we need colon, not inside, but outside for our function. So I think we can go linearly here. So for the derivative, we want this to take our function as well as some value x. So again, I have this pulled up. It's called numerical differentiation, a very simple way, much simpler than jax.jacobian, but this is how we can get our derivative of our function for a finite difference h. In our case, we'll be using dx for h. So dx, again, is the finite difference, or h, they use here in this Wikipedia article. So we can set that to something very small, like 1e to the negative eighth, I think is what we use in class. So yeah, I think I just need a dx. Dx is a parameter, and I said 1e to the negative eighth. So something very small. So we can go over those small distances, see how much our function changes with the slope at that value. I think I just return. So it's our derivative. So I think it's just right here. So f. So we have a function plus that small change minus our actual value. So we have f of x, f1 in this case, since that's what I put in, f1 x plus that dx time. All right, 11 minutes. And then we're subtracting, right? Minus our current value at that function 1 at x. And then we divide by h. So dx is what we're using. So divide by dx. So that's our derivative. Yeah, I think we can just use it like that. And then our Newton Raphson method. So inevitably, let me just go split this. We want to, where are we? We want to use this expression here as our Newton Raphson. So we're going to be iterating that. So we can do, yeah, I can wait on parameters. So maybe x2 is, let's just type it in. x2 is equal to x1 minus our function at that value, x1 divided by our slope. So the derivative of x1, maybe we can just evaluate that outside the function. So derivative of x1, well, let me just write that. I think, can I just do f1 derivative maybe? So f1 derivative, so I'm hard coding this outside the actual root solver. So f1 derivative would be the derivative of our function f1 given a guess at x. So I think I need a value for x, right? So maybe, will it just let me put x? I don't think so. Try. I don't think it's defined. Yep. Now I don't remember what our value of x was as an initial guess, and of course I don't have it. So maybe like 0. Will that work? There you go. So now we have a function we can call with a derivative. Let me just check if this works. Well, let me see it. Okay, so we have a derivative of -5 apparently. We'll see if that works. So we're using that here, dividing by that value as seen in our Newton Raphson. You can't see my mouse. Nope. But here. So we have that settled. I think that's it. So we actually have to loop this. So let me put in, we have to input a function at f1. So this should actually be f1. We have f1, we have an x1 we need to put in for our guess, and then max iterations, right, for our loop. So we will have a loop, maybe 100, I think is what we used. And then a tolerance value so it knows when to stop. So we'll have a if statement. So I don't know, something very small, equals 1e -12 maybe. So those 16 digits of precision are close enough. So this will be looped. So I'll do for I in range, and we can do max iteration. So let me go full screen here. And then zoom in a bunch. So for I in range, so range takes a start and stop limit. We can just do, yeah, 100. And then it should loop all the way across. And then we need a break statement. So if the tolerance is lower, so we want the value to be 0. So the value of our function at this next point, which is 0. So we can do f1 of x2. If that the absolute value of that, since it could be negative or positive. We want it to consider both, so np.absolute value of that. And if the absolute value is less than the tolerance, so it's nearly 0, so that'd be 12 zeros behind. If that's smaller than our tolerance, then we want to break out of the loop. And then to keep the loop going, if it passes that, well, what's happening here? Whatever. We write x1 as the new x2 and keep it going. So that this x2 from up here is the new x1 and gets put in back into the loop. That work? Oh, break outside loop. Does this need to be inside? Something like that. There you go. Watch the indents. And I think we can just do this, right? So Newton 1 at a guess of, so we have our function we need to plug in, and then we have our guess. I think 2.8 is what we used. And I should print out, or I guess return values. So yeah, we'll want to see some values here. So we can do return the I, so number of iterations, return the actual value of x2, so the root we're at. Like, yeah, the root we're at. And then the value of that, at that root, so it should be close to 0. And then we can do the same thing up here. So print that. Pretty please. There we go. I think that's it. See if that works. Oh, what happened? F1. Oh, I forgot some F1s here. So we need to make sure we are using the same function. Whoa, it went all the way to 100? That's not good. So it looks like we're bouncing back between two different roots. What is the problem here? X1, derivative. Should be correct. But we are bouncing back between two values. Looks like -5 and 5. Interesting. Since our root is at 5, so it's taking all the way. Since are we going to a higher tolerance? Perhaps, since a higher tolerance means it needs to run longer. But with practicing this and honestly knowing the correct code, well, I should know it, but this should not be occurring here. So we're not approaching 0 for our function, and then we're not going near a root. We're bouncing to two different roots. Okay, so let me take a look at this and I'll see what I can do. Okay, that's a little awkward. I found that pretty quick, so my mistake. We are not hard coding this. That's the whole reason we have a function. We're trying to find this value at every iteration. It's not just for the derivative at function 1 for an x initial guess of 0. It needs to be for all the guesses, so that's why we have a function here. So we want to put in the function, take the derivative of the function we're putting in, and the current guess. So this should hopefully work. There we go. That looks right. Okay, so quick scare there. I have a feeling this section will be pretty fraught, at least with the coding, will be pretty fraught with some mistakes, so bear with me on that. So it looks like it only took 3 iterations, and we, again, this is honestly already close to the root at 3, which we already had up here. And again, you see the value of that function at the root, so it should be approaching 0. So it looks like at the 3rd iteration, it's pretty much 0 in terms of for our tolerance. So it looks like it rounded off, and we get exactly 3. So that's perfect there. I think messing around with this, you can find out, well, it should give me exact, since it's a root here, that makes sense. But I think if you put in different numbers right here, so we have 4, and then we have roots of 5 and 3. Well, actually, that's kind of equally close to them, but it actually converges at -2.5. So note that your initial guess for Newton-Raphson doesn't always mean that it would converge to the closest value. Again, I had a guess of 4 here, and roots of 3 and 5. However, we ended up converging at -2.5, which, I mean, honestly still works. It's still one of the roots. So just mind that if you're ever trying to do this. So I'll leave it here. Now the next one, a little more complicated. So we'll go back to the iPad here. I love the artistic drawings. So now we're going to move into nonlinear system. So that was a linear system. Oh, well, it was a polynomial. So I don't know, single variable. Now we have multivariable. In our case, we'll be doing a Jacobian. So that's, I think we're actually number 3 already. So that was pretty fast. 20 minutes. Could be faster. Anyway, what's the best way to do this? So with the Jacobian, we're moving into multi-dimensional systems. I don't know what the best way to think about this is. If we have 3 dimensions, or if you're in an airplane per se, let's see if I can draw this. So we have this, maybe something like that, and we move in a 3D dimension. Think of how far did we change from each point, and it's kind of like a point going outwards this way. So that's how I will, in 3 dimensions. I know, not the best drawing, but you can imagine it gets more complicated of how many differences of how much we change from all the different axes or dimensions. So that's this whole idea of the Jacobian and doing this Newton-Raphson method for higher dimensions. So I'm trying to remember. I think we started with our functions. So I think we have actually an example. I might just screenshot it, honestly. So let's move back here. The example is from roots, so an actual root solver. They showed how to do it with a nonlinear set of equations right there. So honestly, I'm just going to screenshot this. Yeah, maybe just this part. And we'll move back. So I need to copy paste it. So right here. Hopefully that works. Whoa. Okay. All right. So this was the example problem. Honestly, you could do this with any problem, but I'm trying to be consistent so I know if I'm doing it correctly. So it looks like our we have 2 equations, and they use x naught. In the coding, we can use x naught as well, so we keep it as a vector of 2 components. Again, they're differentiating between x1 and x0. So we could write this as, well, if x0 is equal to maybe x1 and x2, so just to be consistent. But honestly, it is pretty identical. So if I wrote this in terms of an equation, we would normally see it as, let's see, we have x1 plus 0.5 times, we have x1 minus x2 cubed equal to 1. And then the other component, equation would be 0.5 x2 minus x1 cubed, again, plus x2 equal to 0. So for the root solver, just like we did with our equations where we set them equal to 0, well, for the Jacobian, we'll need this as well. We need to return these as 0 since we're doing the root solver. So we'd move the 1 over to the side, not like that, but I mean, they already have it, but I moved it so it would look like something we've seen before, or how you'd normally see it. But again, for the root solver, we have to make sure the expressions, or the equations here, are equal to 0. So 2 equations, 2 unknowns, degrees of freedom work out just fine. So it kind of does take the same format of our system up here, except now we have multiple dimensions to think about. So this function, we have 2 equations, so that function is now a vector, you could say, of 2 equations. And then now our x components, each of these values actually are 2 different values. So we have the vectors in the future, or I guess the next iteration, which include x1 and x2, and then our variables for the current position, x1 and x2. So I'll write this out. So I wrote out our equations here. So this is, you could say f1 and f2. So our functions, and we can have like big F to show that it's a vector component of both of these two. So I'll use big F without a little bar at the top. And then for our variables, I mentioned before, we have x at the current time or current iteration. So that's a vector of two components. We have our x1 at the current position and x2 at the current position. Same thing with the next iteration, which is what we're solving for earlier. We have n plus 1. So again, following the same format, x1 at the future position or future iteration, and x2 at the future iteration. So if we want to follow this same format we got up here, well, we start with big F, our function. So that's both of our sets of functions I wrote up here. Evaluated at the current position, xn, so that's a vector of our x1 and x2 values. So xn, I use a bar. And then added to that, we have our change in x. So this will be our change in our two variables here from the future iteration and the current iteration. So we can just subtract those element-wise since they're the same dimensions. They're both 2 by 1s. So that is vector xn plus 1 minus vector. So that's the current position or future position minus the current position. Or you could think of it as the current position minus the previous position. But since we're solving for that future iteration, let's just think of it as a future iteration. And then now you'll notice we're missing the derivative. Well, I mentioned earlier that the Jacobian is the multidimensional equivalent of this slope here. So it's that sensitivity to each equation of each of the variables we're solving for. So we have our Jacobian. Maybe you can put a bar over that and then evaluate it at the current time. And of course, this is a matrix multiplication. And this is all equal to 0. So just a kind of representation of what we're looking at here. So we have the Jacobian at the current time, or current iteration. So that is a 2 by 2. So let's write this out. These are sensitivities, so the partial derivatives of each function with respect to each variable. So you can imagine with higher systems or higher order systems with more dimensions, more equations, more unknowns, this gets a bit tricky here. But we have our function, partial derivative of our function 1. So we have two functions, remember. There are two equations with respect to x1. And the next one, function 1 with respect to x2, partial derivative. Then we have on the second row, function 2, partial derivative with respect to x1, and then function 2, partial derivative with respect to x2. So this is matrix multiplied against our change of x. So right up there, honestly, I should have just wrote it under. I don't know why I just decided to rewrite, but anyway, I'll just rewrite that here. And this is a 2 by 1, as we discussed earlier, and element-wise, so we're literally subtracting this minus this minus that. So that would be something like x1 at the n plus 1 position minus x1 at the current position. So same thing for x2, future position minus current position. So you remember with matrix multiplying, we do, well, it follows the form of a dot product. So if we have a 2 by 2 times a 2 by 1, well, first off, we'll have, well, we know this can work since the inner dimensions here match. And then we'll end up with a 2 by 1 judging from the outer bounds. And then one other thing to note, well, the main thing I was trying to say earlier, we have the form, this is a 2 by 2, so I'll write this like that. Matrix multiplied by a 2 by 1, maybe x and y. So this would give you something like, you'd have a dot product in the first row, so we have ax plus by, and then cx plus dy in the second row. So this is our 2 by 1. And so if we write this out, might take a bit, but I think it's good for a visual representation. We have partial derivative f1. Well, I'll show it like this first. So we have this component of the 2 by 2 matrix multiplied by the first row, and the second, I guess, value for the function 1 by x2, which makes sense. We are matching up partial derivatives with their corresponding x1s and x2s. And then same thing happens in the second row for our Jacobian. We multiply like so. So we end up with something like partial derivative multiply by the first row in our 2 by 1 x1. So this is the change from the current and the previous position or future position and the current position, if you want to think about it like that. And plus, so following our ax plus by, same thing, function partial derivative with respect to x2, and exactly the same. So those should be, those are not vectors. I don't know why I tried to do a bar there. So x2 at future position minus x2 at the current. And the bottom is pretty much identical, but we changed the function. So I'm just going to copy this to save some time here, since the focus is on getting this code working. So that's what we're looking at on that, I guess, what I underlined in yellow there. Okay, if that's settled, now we have to do the exact same thing. Kind of think of it in terms of matrix algebra. So we're isolating this iterative term for the future position. So to do that, we have to remember that matrix multiplication is not commutative. So we have to make sure when we multiply our inverse here, we do it in the right direction. But that shouldn't be an issue. So I'll just go ahead and copy this down. So we have more room to work with here. All right. So if we're trying to isolate this iterative term, this future position, we move our function of, well, vector of functions, I should say, big F to the right-hand side. So I'll copy everything down. Xn plus 1 minus xn. Again, negative, don't forget. So it's evaluated at our function. The vector of functions is evaluated at the current position of x. So that includes x1 and x2. So these are vectors. Then to isolate, we multiply by the Jacobian, so the inverse. So inverse here cancels this portion. And then we have to multiply by inverse here. So rewriting, and then I'll also do this at 2 steps like I did in the last one. Also move over our vector of function, our vector of x values, so x1 and x2 of the current position to the right-hand side. So we'll end up with a vector of functions at our next position is equal to xn. So the vector of variables x1, x2 at our previous position minus the inverse Jacobian. And then this is also at the current position. Matrix multiplied by our function, taking in the vector of x's, x1 and x2 at the current position. So that is how we got our general form matched up with our nonlinear system. Again, same exact form here, just isolating for that iterative term. And also notice that, I guess I should preface this with, this isn't actually the way most systems are solved for, even though it kind of seems easy and straightforward. Of course, this idea of using the inverse is actually actively being avoided in most algebra for solving systems like these, higher order, higher systems, and mainly can only be done for, I don't know, toy problems like this, where we have around 10 equations, 10 unknowns. Again, there's methods out there actively avoiding this idea of the inverse, since you can imagine the inverse gets pretty big. So trying to calculate it, and even though multiplying like this makes sense, it's just inefficient and isn't the most robust method out there. So with that out of the way, I think we can just code this out. I'll be using that root solver again example. So let's switch over here. That is the wrong one. This one. So, all right. Again, this is from the API reference of root solver. So if you just Google SciPy optimized root, scroll down, you'll have our example problem right here. And again, this Jacobian is exactly what that jax.jacobian is what we'll do. It's doing this partial derivative. So more on that a little bit later. I don't think I need this anymore. So hopefully, okay, we're still completed and I already imported it. Perfect. So now we just start our example. So actually, I think I can just copy paste this. So we already have the import. We will want to change our function. So function 2 perhaps. And remember, x is now a variable. We'll keep the arrays here for our, again, it'll be referencing x1, x2. However, we'll also need to change this to a J and P array because we will be using that jax.jacobian. This iPad, whatever. So J and P array of all of that. And we'll just keep those expressions since it's harder to type them all out. And x will be, shift enter on that. X will be a vector, do J and P array again of, I don't know, 0.1 and 0.2, what we used. So if we do the jax.jacobian of this function, it's effectively the same thing as doing this derivative, but you'll notice that it was the partial derivative, and look at all that coding that was done. Of course, you can do it manually, do it by hand, whatever, but again, jax.jacobian does it so much faster that there's no reason not to use this. So if we do our f2, well, let's just do it first. So jax.jacobian of our function 2. We don't have to specify. Oh, did I not? Oh, f2. I don't know why I put function. Let's do f2. So notice we didn't have to specify the parameters. There's only one parameter, and it does it automatically. So this idea of automatic differentiation, again, Jax is from AI, what Google uses. So anyways, so this, we want to do the, well, we'll just call it f2, the jax.jacobian. So jax.jac, about that. And then now we can plug in any values for x. So it takes in the same parameters. If you've read that little blurb underneath, it'll take the same parameters. And I need to put x there. So let's do that again. It takes the same parameters of our function. What am I doing? of our second function. So again, our second function is the big F we saw in the iPad earlier, what I drew up. So this is a vector of our functions, and then our Jacobian takes the same parameters as this function, and now we can plug in our x, and it should give us the exact same thing if we copy paste this thing. So again, it says it's the Jacobian. It did it by hand in that example. So let's do it. Copy paste, evaluate at x. So those are our numbers, and if we evaluate this Jacobian from the example at x, it should give us the exact same thing. So again, save this the hassle of trying to do, well, for one, code this out, and two, actually do the derivatives by hand. So thank you to Jax for that, jax.jacobian. And you'll imagine partial derivatives get a lot more complicated with, again, higher order systems. Imagine for the distillation column, when you have multiple unknowns, multiple stages, and the equations, well, you'll have to do partial derivatives of all those equations for all of the unknowns. And remember, we have that NRTL thing that we coded out a long time ago, but it was very hard, mathematically speaking, in terms of trying to do a partial derivative of that. So trying to avoid that at all costs. So that's why we did our Jacobian here. So I'm just going to go ahead, delete that. We don't need it. And we will need to do, we won't hard code it. Again, that's why we have the Jacobian. We'll be plugging it into here. So speaking of, I think we can just copy paste most of this, right? Newton 2. So let's change what we know. So it'll be a different Newton Raphson, a different function. Technically, none of this needs to change, but we're going to be consistent to be explicitly with this new function. Iterations are the same. Tolerances should be okay. Range is okay. So now here's where it gets different. There is no derivative, so we should, outside the loop, take the Jacobian of our function. Doesn't have to be f2, so we could do just some function maybe. Just function jax.jac, and then take it of our f2. Again, it doesn't have to be f2, but if someone were to plug in a different function, we want to make sure this root is still working instead of hard coding it. So, and it also works through the iteration loop. So we have the Jacobian of our function, same range. So let me break this out a bit. We have our values for x2. So these are vectors. X1 should be fine. I know I put x, but it should be okay. Derivative is where we're not doing a derivative. And then if you remember, I'll do a split screen here. Where's my OneNote? We did, 40 minutes already. Where are we? Here. So we did a inverse with our Jacobian. So I believe, so this is f1, x1 corresponds to big F and xn right there in yellow above my head. And we matrix multiplied. So we have matrix multiplied of our Jacobian, what we want it to be. So f jax.jac, but we want it to be the inverse. So we do the inverse. JNP, I think it's linear algebra, then inverse of our function for our Jacobian. And does the Jacobian need to take in any variables? I think it just takes in the current x, so just do x1. Then, is that it? f1, x1, so this should be f2. I changed it all to f2. Okay. There we go. As I was being explicit up here. Else do we have? Printing it should be fine. Yeah, it won't be an absolute value this time because it will be a set of two components. So instead we should do the norm. So think of it as, well, in our case, it's two components. So this could be thought of as a vector. If you take the norm, so the norm is the JNP linear algebra and norm. Yes. So we take the norm of that. I just do that. Yep. And the norm is all the components, well, in our case, the two components, each of them squared and added, and then square root. So I don't think this is the first time we've done the norm, but just a quick review or tidbit, I guess. And then if that's smaller than the tolerance, so the length of the vector is smaller than the tolerance, then we break out of it and then we loop back through. I think this should be good. Okay, let's see. F2 and then X, right? X right there for our initial guesses. Newton 2. Please work. Okay, got it in 5. So I did it all on split screen. Here we go. So we have roots. We have our iterations. Took us 5 iterations, and we have the roots of that. So let's see if we got it. They plugged it in. 0.841 and 0.158. Perfect. We got it exactly. Awesome. And then we also return the values of our x's. So these are approximately 0, -17th. That's a 0 on my book. And it should be for our cases here, or for our uses here. All right, I think we can go back to drawing board and make our way back to what I think is the hardest one. So I think we're actually, let me check these off. We've actually done almost all of these. Now we're going to be talking about the last two here, this Thomas algorithm and tridiagonal matrix. So let's go back to the collab. We're done with this. And now we have this idea of tridiagonal matrices. So We'll be using the Thomas method. Does that even show up here? Let's do Thomas method. This is one of the ways to solve the tridiagonal matrix. Oh wow, there you go. This is what it looks like. I don't think this is the first time we've seen this. We've done this with Crank-Nicholson, the stability analysis of that bar where the heat was transferring from one side or from both sides to inwards, I think. So yeah, we're going to be using this idea of the Newton-Raphson to help us with this. It kind of follows the same format. If you think of this as your vector of components, well, this is essentially our Jacobian times our change in x, so our positions from the current and future position, and then our equations on the right-hand side. So this Thomas algorithm lets us backtrack by using back substitution once we complete it in a sort of manner where we have, I don't know if it shows here, but we have ones that go across the diagonal. Close. I have code. All right. Well, I think you get the general solution. So this goes up to the nth, however many equations, unknowns you have. I'll do it up to 4 so we can visualize it, and the algebra gets a little tricky, but it's actually done pretty fast on the computer here. But yeah, I don't think it shows it, so I guess I'll have to draw it out. Sure. Switch back. Okay, almost there. All right. So if you think of it, where are we? Somewhere here, right here, I guess. Even though I wrote out, let me erase these inverses. Let me prop this up. So if you think about it, we're kind of looking at this. We have our equations on the right-hand side. We have our change in x's, which was that column vector of x's you saw in the Wikipedia article, and this Jacobian, the partial derivatives, on the left-hand side. Follows a similar format where we can do let's do a 4x4. So let's write this out. We have our coefficients. B1, yeah. C1, 0, 0, so 4x4. So we have a diagonal. A2, B2, C2, 0, and you'll imagine, again, with more values, zeros will perpetuate until we hit, well, however many dimensions it should be. So we have 0, A3, B3, C3, and then 0, 0, A4, B4. So notice that A and C, the upper and lower diagonals here, have less values, or I guess number of values for compared to B. So if 4 was the number of stages in our distillation column, C and A would both have n-1 values. So did I say n was the number of stages? So n equals 4 in this case is the diagonal, and also however many we're going down. Then A and C would be n-1, so 3 for both. So that would be matrix multiplied by a column vector, x1, x2, x3, x4. And of course, Python indexing starts at, or NumPy indexing, one of the two, starts at 0. So these would be indexed as 1, 2, 3, 4, or 0, 1, 2, 3, sorry. And then all of that is equal to our equations. We have E1 epsilon, so all the way to 4. Of course, the algebraic way to show this would be something like, let's see, we have B1 times x1 plus c1 times x2 is equal to epsilon 1, or equations of 1. You have a2 x1 plus b2 x2 plus c3 x, or I'm sorry, c2 x3 is equal to epsilon 2. And then 0, is it worth going all the way? I'll just do it for this. So we have A3, X2. Notice I'm keeping it in terms of the X in the same columns. Just so you can see how it's kind of going diagonally here. And then B2, X3 plus C3. What am I doing? These are threes. C3, C3x3, C3x4 equal to epsilon 4, or 3. Maybe I'll move these two. So you kind of see takes the form. It's still in the form of a matrix. So these are zeros here. Plus 0, plus 0, plus 0. And now you have zeros. And now it's just A4x3 plus B4x4 equals to epsilon 4. Notice that the B's always have the same, I don't know, index as their corresponding X's. The A's have one less, and the C's have one more. So you'll imagine for the nth order, you had A, N here. So this would be Xn minus 1, Bn, Xn, etc. And of course, epsilon n. So that's what it would look like algebraically. Now we're trying to solve for all of those X components. And to do that, I'll move that to the side. We can do something where we kind of ignore, not really ignore, but we focus more on the leftmost matrix and the rightmost matrix. So we would have something, let's see, we have B1, need to make sure I have enough room for this. So B1 plus C1 is equal to, I don't think that's enough room. Let's put all the way here. So that is equal to epsilon 1. So we can call this our first equation. And one of the first steps we take is to divide by B1. So divide by B1. That would net us 1 plus C1 over B1. So I guess these are technically 0. And we have epsilon 1 over B1. I'll write the next row here so it kind of looks easier to subtract out. So again, our goal here is, where's the best way to write this? Maybe up here. So I'll just draw an arrow. Hopefully this makes sense. So we're trying to get those rows of ones. So it's easier to do the back substitution. So something like this. We can call these will be modified values. So I'm kind of getting ahead of myself, kind of spoiling it, but we have a 4x4 and ones going down where the B used to be. This will be modified value multiplied by x1, x2, x3, x4 equal to epsilon 1, 2, 3, 4. And you'll notice that now it is very easy to solve this set of equations when we know at the very bottom x4 is equal to epsilon 4. So we can do that with I'll do a concrete example. Is it worth doing it now? I need to show this part first, but yeah, I'm sure I'll remember, hopefully. So I was rewriting before I got ahead of myself. So we have equation 1, I don't know, rows, I guess, even though technically they're not indexed correctly, but that's how it makes sense to refer them to like in that way. So we had A2, B2, so A2, B2, C2 is 0 plus 0 equal to epsilon 2. So is it worth storing these values now? Man, many decisions here. So yeah, we could store them as we go along the way. So I don't know. I think it's just worth, since most of the middle here, this middle vector stays the same, but this gets changed to a modified version of itself. So I don't know why I wrote just E there. But these should be modified as well. These are modified. We can do stars. And I put stars on the left-hand side, but these are all C's. So C stars if you want. C1, C2, C3. Let's just do it one at a time. I'm getting cross-eyed here. Okay, so this is number 2. The next step here, still 1, but we do the second step. We want to subtract it, or multiply, I'm sorry, by a2. So multiply by the next iteration of a. So I don't know, ai plus 1 maybe. So that would give us, going down here, a2 plus a2 cb1, c1b1, sorry, plus 0, and then a2 e1b1. Okay, now the last step here for our first equation is to subtract. So it'd be 2 minus 1. So if we subtract these two, we would get something like 0. Come on. What is happening? 0 plus b2 minus a2 c1b1 plus c2 plus 0 equal to epsilon 2 minus a2 e1 b1. And notice that these values are coming from the previous step. So this was our third step. These values are coming from the second step. And you'll notice this also keeps iterating. So if we do this for the second equation, so our first step, so let's label this as 2, and then we can go a, where we divide by the b term, divide by b. So this is our b term here, and we'll divide all across. So it would be 0. Please see this okay? 0 plus 1 divided by itself, and then c2 over this funny looking thing, b2 minus a2 c1 b1 plus 0 is equal to, of course, we have a big one, e2 minus a2 e1 b1, all divided by this modified b term. So I'll be calling that in the code, I think b mod is what I used. So c1 b1. So now, second step here, what did I do? Multiply by the next a term. So let's write out our third line. We have a3, b3, c3. So a3, come on now. a3, b3, c3, kind of running out of room here. And of course, this is epsilon 3. This is equation 3, row 3. Of course, the indices will be -1 in Python, so we'll have to account for that. So multiplying by the next term of a3, we have, I'll kind of scrunch up the columns here, but 0, we didn't subtract it, so this is still a3. Then we have a3 c2 or c2 over b2 minus a2 c1 b1, and this is still a 0, and then a3 in front with this modified epsilon value, epsilon b1 b1 over b2 b1 b1. So yeah, this keeps on getting crazy. Again, we've only done this for 3 equations, and again, you'll know how difficult this gets with more and more, higher order matrix. So this is, next step will be subtracting. So 3 minus 2. So kind of almost there, but we have 0, 0, b3 minus this modified c value. So a3 c2 b2 a2 c1 b1. Again, these are all from previous steps. And then we subtract the epsilons. So epsilon 3 minus this abomination, epsilon 2 minus a2 e1, copying all down. So hopefully that gets the point across. The main things to keep of note here are how in our matrix, we only need to keep track of these C values as they change and the epsilon values. And also with our top row and bottom row, these are kind of special cases. What's happening? Did I write out the bottom? Okay. So these we won't necessarily need to do a loop for, since they're a bit different. They don't have that A term. So for the top term, we can just hard code out our top term. First row, we can hard code that out to be dividing by the C1 over the B1, epsilon over the B1. So we're trying to achieve this format. So I think I can just erase this, honestly. Fill it in with what we know, since we kind of went pretty far down already. I don't think I did the final C term. This is technically, is this 2C? Is that how I labeled it? Should have been better at labeling here, so now we just called it 3A or 3A, yeah. And we multiply by A2 in front of all of that. So notice that if we want to achieve these values of 1, well, we divide C1 over B1 for this first row, so that's just C1 over B1. And then epsilon was, get that modified value, epsilon 1 over B1. Here's where it gets a little tricky. So to get a 1 here with our B, we had to multiply the A term to the top, and the top row had to be divided by B1. So it would be C2 over this modified B term, which we divided by 1 already. So it would be, let's see, I don't know, I'm trying to do it in my head when it's already done here. It would be right here. It's a modified B term, and then this is our new C. So C2 over B2 minus A2 C1 over B1, right? A2 C1 over B1. Same format. Well, for the E, it's a little different. The E we had to subtract from the previous one, multiplied by the current A, so A2, E1, B1, and divide it by, I don't know, it's this value here. So B2 minus A2, B1, B1. Again, notice the pattern where we have this term, the modified E and modified C, already from the previous row. So we'll be storing those as arrays for the modified C and E values. C here, I think we did this already. Is it worth doing? Yeah, we can show it. So it'd be C3. I don't think I'll write it all out, but C3 over the next modified B. So this would be modified of the third row. And same thing here, E3 minus, I mean, technically, how do you want to say this? You'd be subtracting from the previous row multiplied by A. So it'd be A3 times, I don't know, E3 star. We're using this as the basis. So all of this, essentially. And then all of that divided by the modified version of B3. So star. And hopefully that gets the point. And then for the last row, we'll do this outside the loop. So we won't need to code another C, but it follows the same format as the one above. So it would be E4 minus A4 times the previous. So I don't know. What am I doing here? E2 modified, right? Because it was modified by multiplying. First you multiply by A and you divide by B. So that's the modified for E2. What else? I don't know if it's worth showing that this is equal to B2 modified. So again, it looks very messy. So we have E4, A4, says this would be E3 modified over the modified B. So B at the current row would be B4. Okay. Hopefully that kind of makes sense. I think it'll make more sense once we actually code it as well. But now for the more concrete example, we're at 1 hour. Okay. So to actually solve this, why do we go through all this effort to get it in terms of ones? Well, again, I mentioned that now we have this simple equation where back the bottom row is equal to just x as the modified version of itself for epsilon on the right there. So let's write this out for something simple. We'll do a 3 by 3, some simple numbers. Hopefully my algebra is still good at 4 in the morning, but we'll see. So we have our diagonals of ones here. Fill this in with 2 and 3, why not? And a 0 here. So that's our same format as the one here where we plugged in values, but now we're doing a 3 by 3. We have values x1, x2, x3, and those are equal to some values. Let's say, is it too easy? Let's do 2, 1, 3. Sure. So now x3 is 3, so we can write that as true. So we go from the bottom up. So we have a 1 times x2, I'll just write it like this, plus 3 times x3, and we know x3, and this is all equal to 1. So if x3 is also equal to 3, or if x3 is 3, excuse me, you have x2 plus 9 is equal to 1, so x2 must be equal to 1 minus 9, which is negative 8. For the final row, you have, let's see, x1 times 1 plus 2 times x2, where you know x2 is negative 8, equal to 2, right? So equal to 2, equal to 1, equal to 3. 3, 1, 2, okay. And then 1, just double checking here. 1x2, 3x3, 9, 1 minus 9 is negative 8, okay. And then x1 plus 2x2 is equal to 2, okay. And if that's negative 8, this is 16, negative 16, x1 equal to 2. So add 16, x1 is plus 16, 2 plus 16 is 18. So it's pretty easy now that we have all our values. When we know this bottom row, we have that simple, I don't know, equivalency, if you will. So we'll need to code this out here. Know the best way to, let me just do this now so I don't have to later. Essentially, these are this green values where our C's. So this would technically be, let's write this out for in terms of values here. So we had our, I don't know, x3 is equal to epsilon 3 modified. And then we had x2 ended up being, so plus 9 is equal to 1. So 3, what's the best way to write this? You had x2 times our current b, which is a 1, so don't have to worry about it. It's always 1. Plus a 3, so that's our C star modified. So C star at the current position, current row, x2, and that was multiplied by x3 is equal to epsilon 2. So to isolate for this x2, you would have epsilon 2, and of course is modified, plus or minus C star 2 x3. So the next iteration of 3. And this would be, well, let me write in a general form here. We had xn is equal to epsilon star at the same position, C star at the same position, times x at the next position, n plus 1. So this is what we'll be using at the very, very end. I think we got it. Yeah, let's just try this out, see if it works. So let's go to the collab. I need these. I don't need this. So diags here. I'll do a new notebook. Why not? So new, where is it? Sip here. Oh my goodness. So this, what do we want to call this? Tridiagonal matrix, Thomas method. Tridiagonal matrix. So I think all we need is numpy, so import that as usual. I do have a random seed, so that was from earlier. Let's not do that. Let's split. And one note here. Those were all the random code we saw earlier, trying to help me out, honestly. So this random state, if you have ever played Minecraft, it's the exact same thing, honestly. Between computers, it won't give you the same thing, but essentially it's giving you whatever random numbers you generate will be the same for the first time you do them. So let me copy and paste. I don't think so. Great. Okay. So R&D is equal to np.random state. Well, s. And then we have 4, 2, 1, 4, 1, 3, 4. So this is the code our professor used, Carlos, or Minecraft seed, so it generates the same random numbers each time for the first occurrence. So very similar to Minecraft where you load up a seed, it's the exact same thing. All we need is that, so what happened? So let me go back, full screen, delete that. Let me just check. 4214 4214 134 421. Okay. So we set up our problem with some random integers. I think we use 1 to 10 as our range, so something like R&D random integer from 1 to 9, so we don't count the 10. And then we do it for n number of times, so I need n number of stages, or n number of whatever rows, dimensions you want to call it, for our matrix here. I think we use 5, and then I'll put 5 here. So we have a random occurrence of integers, and then, of course, why did I put 5? It should be n, so we could change. If I do it again, refresh, it'll be different, of course, each time. But I think the order does stay the same in between all of them. So anyways, let's reload. Go back to our original set of numbers. So if we want our diagonal with that tridiagonal as such here, there's a way we use numpy-diag. So I think we use this for Crank Nicholson. We supply a 2D array, or no, a 1D array, and return the 2D array with V on the kth diagonal. So it's going to give us a diagonal or a matrix with this as its diagonal and as a 5 by 5. But it'll index at 0 to 4, of course. So go numpy-diag. I think we can just do this since k is set to default 0, and of course it refreshed. So this is 71367, original set of integers, and now it is the diagonal. And now let me put k there. So notice that if I try to move it to the upper diagonal, it'll shift up. However, since it is still at 5, our number will be increased to 6 by 6, since now there are 5 integers on the upper diagonal. So to do this, to prevent this, we want to have n-1 for the upper diagonal and n-1 for the bottom diagonal. So again, if I do -1, that'll be the lower diagonal, but it's still a 6 by 6, which is not matching our number of stages up here, this is to denote the diagonal length as well. So we'll do n-1 for those. So I don't know if it's worth being explicit. Why not? So we have upper, mid, lower, something like that. And we want this to be equal to our random integers. Dude, I don't know. The problem is if it will be generated in the same way. So I'll try it this way, but I don't think it'll work. But we'll see. So I'm just going to copy paste all these and make sure they're the correct amount. So this should be n-1 for the upper, and it should be k equals 1 and go up. Middle is the center diagonal, so 0. N is fine, and then n-1 for the lower, and then -1. So let's see if this loads up. And let me add those up. So upper plus mid plus lower. Of course I can't see it. So A, do this. Upper, mid, lower. It's like a exercise. Okay. Display those. So of course they're different, but there are 1, 2, 3, 4, 5. Okay, so they're all 5 by 5s. But the integers are different, so I might have to do it the same pattern. But if we add them all up, you'll see that we have all 3. Oh, what do you know? This works. Not quite. Okay. So it doesn't give me the numbers I want to see since I'm trying to be consistent. So I'll actually do something like this instead, where I'll just copy paste all of them. So this was for the visual effects. You'll see the bottom, center, and upper. We can just add matrices just like that, and you'll have all 3 there. So I'm going to delete all this and just make it what we had, I think the same, what I practiced and also what we saw in class. So I'll just copy paste these, honestly. And I think we started with the center diagonal, and then we did the n-1 for both, since they're both less than the mate diagonal, and then it's a -1 and 1 or 1 -1. I don't know if we did the upper or lower diagonal first, but we'll see. Come on, I want you to display. I'm gonna rerun again. Oh, there you go, it worked. I think it worked. 1, 7 is what I'm looking out for here. I don't know. 5, 7 is right, so I don't know anything about the... Well, if this is right, this is the bottom diagonal, and if this is right, this is the top diagonal. So hopefully that's right. Then we also want to do the same thing for our equations, but this is not the modified version. It's just the e's. So let's call it e, and then make it also a random integer. RND random integer. And we also do 1 to 10 for the same number. Well, let's see if that works. Rerun, because if I rerun these, it'll give me different numbers. So, all right, I think that's right. So I think now we need to code out the initial values. Wow. Okay. The modified values, I should say. So again, this is B1, this is C1, this is A2, B2, C2, A3, B3, C3, and so on. We're solving for the invisible X column vector here. And of course, I mean, you might want to make that look like a column vector, but that's our equations on the right-hand side, those epsilons you saw earlier. I think there's a way you can just kind of see the answer key, quote unquote. Here, you can do something like, is it NP linear algebra solve? And then we just plug in our matrices. That looks familiar. So these are the values of our x. After we just have a hard-coded function in NumPy that solves matrices just like that. Given obviously 2 matrices. Yeah, we'll be trying to achieve this with our hard-coded, I don't know, our own tridiagonal matrix solved with the Thomas method with back substitution. So let's do, we can have zeros of our modified values first for both those arrays, since we'll be needing to store them, as I mentioned before. So C mod maybe, or C star. Mod. So that is a array, zeros for now. We'll be plugging things into it later. And we'll make it n-1, since remember the C's only go, this is our C's, it doesn't reach the last row, so it has to be n-1, 4 in our case. And then same thing for our epsilon, their modified values, but they do go all the way down. This is what we need to note when we do them for the top and the bottom separately outside the loop. So, okay. Let's see here. What else? So we need to set the initial values. So those will be, remember our first one was B1 over C1, so 5 over 7, and then E1 over B1, so 4 over 7. So let's do this. 5 over 7 and 4 over 7 is what we're aiming for. And we want to get the initial values, or the first values, I should say, of both these arrays. So we index at 0 for both, and we do kind of hard code in that diagonal here. So for our C mod, the modified value is B1 over, or C1 over B1. So that is column row, or I'm sorry, row 0, column 1 for the C1. So row 0 of our A matrix, column 1 divided by, now we have row 0, column 0. So the origin point, if you want to call it that. So both are going to be divided by, so that's our B1. And this is the modified version would be E1 divided by the B component. So 4 over 7, that would be E at index 0. So E at index 0. Let's see if that matches up. I need to display it. Call it, however you want to say. So we do that, and voila, it matches up perfect. So we know that's right. I'll leave it. Is it MZ? Yeah, I'll leave that. Now we have our loop. Got to be careful for our indexing here. So we need to make sure we're looping from these portions only, since this, again, I mentioned the top and bottom rows are special. We hard code those out of the loop, but these ones we can code inside the loop. So this would be, I think we just do our loop, right? So it's just for I in range. What is our range? We want to start from, let me move the column A here so I don't have to keep looking. We start from 1 all the way to 3. So I could just put 4. That would work. But yeah. So again, we exclude the last value, but we want this in terms of n in case someone decides to change it. So what's the best way? We would do 1 to, I don't know, n minus 1. Would that work? But it needs to go all the way down. Well, this is the stopping value, so it should end at, it should go from 1. Well, this is incorrect since this is starting at 0. We want it to be 1, 2, 3. So let me think about this. This is starting at 1, n is 5, 5 minus 1 is 4. So this should go to 3. Yeah, 1, 2, 3. Perfect. Next thing we should do before we get carried away, we need to extract our current values of A, B, and C. Do we? Well, for one, we know we need the modified values, so let's do that. We will also need to store the new values of C and E at the current index, right? So I think this should be at the current index. They'll be changing. We're storing them as they go. Oh yeah, we will need A, B, and C. Unpack those from our matrix. So it's a little bit complicated. Again, with the indexing, we have to watch ourselves. So this is at the current row. So we're unpacking this. At the current row is for our first range. I don't know, however you want to say. So I do from range, the current row. So if you think about it, if you do I, so in our case, we're starting at 1. So I would be 1, 1. So row 1, column 1. So notice that I is the center of the diagonals here. So this would be the I's, the diagonals. Those are our B's. So I is actually our B. And then actually I might want to comment this out so I can see this. What was it? Like that. So let me zoom in. Is that too much? Wow, my voice is getting hoarse. Ugh. Okay. Trying to index this, and then indexing stops. Actually, let's think about where it starts. So this is I. We want I minus 1. So I minus 1. That's our first range. Our starting point for our range, and then our ending point is, so this is I. This has to be I plus 1. But if we do I plus 1, it won't take I plus 1, remember, because this is stopping at 4, and then we stop at 3 here. So we should do I plus 2. And then let's print this out. Perfect. 715 935 561. That is beautiful. Okay, that's working. Okay, keep watching the index. I don't know why I did that. I can just do it like that. So the B mod will be. This is where the OneNote comes in handy. Let it. Oh my goodness. Okay. Are we here? So, right, we have our modified B value. Can't see my cursor. Modified B value. We need that because we're going to divide our C by it, and this is our C modified value. So that we already have our first one, and then we can use it here. So those are modified C values. And then for our epsilon modified values, we have E1, B1. We already hard-coded that up here. But for the next value, we have E2. So all of this is our modified E2 value. So we have to multiply the current E2. So up here, our current E2, 5, minus our A2, and over are multiplied by our previous E value, modified value, divided by the modified B value. So there's that B2 that comes back. So this B2, well, B star in all cases will be the current B minus the current A. So those are the same index, so that's why they're current. And then multiplied by C1 over B1, so the previous value of the C modified value. Yeah, C1 over B1 times C1 over B1, which is the previous modified value at, so that would be I minus 1. And if it starts at 1, we have 1 minus 1 is 0, so it gives us C1 over B1, which we already did, so that works out. C modified at the current row would be the current C, so C2, current C, minus or divided by the modified B. So again, this denominator right there is the modified B, so divided by B mod. And then the epsilon here, a little messy, but you have the current E. So the current E is E at I. Well, we already did 0, so it'd be E at 1, or E at I, where I starts at 1. E at I. So that's the second component. E1, indexing. Again, 0 to starting at indexing starts at 0, so the second component of E would be 1. So that minus the current A, we're at A2. Right? Yeah. A1, B1. Yeah. This is, we are at row 2, so this is A2, B2, C2. So A2 times, this is E1 over B1, the previous value of E mod, so we can do I minus 1. And all of that divided by B mod. Wow. B star, so B mod. I think that's it. Okay, didn't yell at me. Perfect. But we should have values for our C mod and B mod, or E mod. We should be missing 1 for our E mod. Yep. Since that's the bottom portion. So the bottom portion, we have this 1 and 7. This is A4, B4. Down here, what we're trying to get is a 0 and a 1. So we'll have to modify our epsilon here. So that's why we're missing a modified epsilon value at our, so it would be the 5th position, or indexing at 0, 1, 2, 3, 4. Makes sense. We're missing E4. So that being said, we have to hard code the bottom row. So I think we can copy paste this, but we'll be modifying many things. Yeah, I don't think we need the split screen, so that. So let's pull up the matrix. So we're looking here. We don't need to keep track of a C since there's no C. So our indexing will change here. We're not I's anymore. We're at, so this would be 0, 1, 2, 3, 4th row. So n minus 1. So can I think I can get away with doing, by multi-cursor, change all the I's to n minus 1. And then, well, this indexing needs to, well, this gets simplified to n minus 2. Can I just do, there we go. We have 3 instances, so n minus 2 for all of those. Our indexing here is a little off since this was ending at C. Now we only have values for A and B. And remember, our diagonals are, we replace I with them. We replace I with n minus 1, so our diagonal is now n minus 1, which makes sense. This would be 4, 4. N minus 1, n minus 1 would be index 4, 4, which corresponds to, well, 0, 1, 2, 3, 4, row 4, column 4, 0, 1, 2, 3, 4. So 4, 4 makes sense, n minus 1, n minus 1. However, indexing excludes the last value, so it won't be n minus 1, it would be n. So let me check that. Don't trust myself. Is that? Oh, we're still shifted over. So let's check A and B real quick. It should be 1 and 7. Beautiful. What else do we have? The modified value of B should be the same. We already changed the indexing. Is that correct? N minus 2. 4 minus 2 is 2. The modified value. Honestly, I'm going to just trust I did this correctly. The B's, I guess the calculations made in the loop still apply to the bottom value. We just have to be careful about the indexing here. There is no C modified, as we mentioned earlier. And then now we're taking n minus 1. So 4 of our emod would be, did I delete the emod? Of course I did. We're missing the last one, remember? So we need to reference. So it'd be 0, 1, 2, 3, 4. N minus 2 would be 3. So 0, 1, 2, 3. We need to reference previous. Oh, this is for CMod. I'm talking about E here. So this would be the current value of the E, which is n minus 1, 4, 0, 1, 2, 3, 4. Currently 0. And we do our same exact calculation up here that we saw in our OneNote. Honestly, why not? Yeah, why don't? Yeah, let's go for it. Okay. So, solve this. Let me bring down our NP. Yep, solve. So this is our solution. Given everything goes correctly, we should get the exact same numbers. So we'll need a loop, but to start, need to set our x values to something. So that'll be a bunch of zeros. Yeah, zeros. Can do it for, it's just n. It's the exact same up here, right? Yeah, so this time x is it goes from the full numbers, so it excludes n, so 0 to 1, 2, 3, 4. And then we do our loop, so for x in range, or I guess. Where are we going? Well, I always need to bring this down. So, well, actually, we already know this value, so x at -1. Remember how we saw that over here? Our value for the last component of x was equal to the modified value, the last modified value of our equations on the right-hand side in red. So that's exactly what I'm doing here. X -1, the last value is equal to the last value of our modified right there, like so. And then for range, we want to do these three again, or I guess looping up from the second to last row up. Let's see. Would it be n minus 1 to 1? But we want to include 1, do we? Let's see here. N minus 1 is 4. Is that right? 0. We want to be 3, 2, 1, 0. So to do that, well, for starters, we're going backwards. So indexing in a range takes start, stop, and I don't know, step, I guess. So we're moving backwards. This is -1. Our stopping point, if we exclude last value, should be 0. However, with indexing, yeah, this should be -2 if we want to do 3. So 5 minus 2 is 3. Start at 3, go all the way down. So this should be 0. So n minus 2 goes to, should hit 0. So it's -1. Am I overthinking this? Let me just look at this. I think I'm overthinking. Oh, yeah. No, okay. I don't know what I'm thinking of. So 3, 2, 1, 0. Remember indexing row 0, row 1, etc. So that's correct. And then we just plug in our x values we saw here. Now you know why I did all that. So we have x at the current position happening equal to e mod at the same position, I minus c star, so c mod at the current position times xn plus 1, so this is x at the, I guess technically previous, but future position in this case, so future I plus 1. And hopefully we give it x. Please be right. Oh, we have a mistake. Okay, here we go. Let's have some fun here. Is it worth? You know what? I'll pause it here. It's getting pretty long. Wow. Okay. Yeah, I'll find this mistake real quick. Okay. That was awkward. The first thing I did was run it all again, and it worked. So, yeah, I have no idea how to go back. Let's see. I think I can go back. Well, if I go back, I don't know if it will. What is happening? I can't even see. See, now I'm scared to go back and it'll delete all my progress. So I could save it. Let's see. If I save it and then revisit the old one. Well, do I have revision history of this? Nope. Well, this should all work, but let's see. I'm trying to show that I didn't change anything, but I don't think it's nice enough to let me do that. The last minute, maybe. Eh, yeah, let's see. Copy paste what I just wrote. And then it'll show me. Oh, okay. Well, whatever. It just works, I guess. Trying to troll me when I'm almost done. Okay, well, that was easy. I'll just keep my original, like so. Yeah, that was it. Um, I don't know if we need a rundown. I feel like this is crazy long already, but yeah, we achieved the same values as the NumPy linear algebra solver, so means we have to be correct, right? So again, we were iterating using what I did off the split on that one note where had our example, then we had our middle loop, we hard coded our bottom and top row, and yeah, honestly just did the diagonals, so same thing as what we did in our lab here. So I don't know. I don't think it's worth explaining given the length of the video right now. So hopefully everything made sense, and it looks like I got everything done here. So I believe we have one more video, final video of this class, but yeah. I don't know. I don't know what else to say. I don't feel like I'm missing something, but yeah. Hopefully that's all good. Okay. Thanks for watching.